Now we reviewed taking indefinite integrals with u substitution, but now we want to review taking definite integrals with u substitution. So what's interesting about this is that when you use your u and you have du here, then these are now u values. See, the thing is that mathematicians don't bother to tell you, but when we originally write an integral, having the differential here means that these are both x values. So this is x equals b, and this is x equals a, and that's implied by the notation. But now, because we're doing this with respect to u, this would mean that u is equal to g of b, and u is equal to g of a. And you can find the integral that way. All right, so the important part there is that you need to know that you need to change your limits when you're using u substitution. When you change those variables, you have to change the limits as well. Remember, you can never mix and match, right? Never allowed to mix and match. So you must change your limits of integration as well. In case that wasn't clear. All right, so let's do one. Now, this one's a really simple one. I grant you we didn't actually have to use u substitution on this. I mean, it'd be pretty easy to distribute the two and just integrate it, but I'm going to make a point here. So, rather obviously, u is equal to 2x plus 1. No problem. The derivative of that is 2 dx. Well, yay, I've got a 2 and I've got a dx in there. I don't even have to mess around with that. Lovely. Now here's the trick. This is an x value. It doesn't say it, but it does. So it might not write x equals 0 right here, but this differential being right there implies that it is x. So when x was equal to 0, u is equal to 2 times, let me put it this way, u of 0. U of 0 is 2 times 0 plus 1, which is 1. And then when x is 5, or excuse me, x is 2, u of 2 is 2 times 2 plus 1, which is 5, which is what I was thinking of. Okay, so now when we rewrite, we have to rewrite our integral using all of these pieces. So we write it as the integral of u du. It's a very easy integral, but u du. And instead of writing 0, I now write 1. And instead of writing 2, I now write 5. Those are u values now. I just can't stress it enough. You must change your limits of integration. Right? And that's what I'm doing right here. This and this are because I must change my limits of integration. That's why I'm doing such a basic problem here to have us practice that. Okay, well, the integral of u to the 1 power, which is what this is, would be u squared multiplied by a half. But then I'm going to take that value from 1 to 5. Okay, so from 1 to 5, no problem. So then I can substitute in. So that would be equal to, and of course the 1/2 can just kind of come out in front because it's constant. So it's 1/2, and then it'd be 5 squared minus 1 squared, which would be 25, take away 1, which is 24. So this is 1/2 times 24, which is 12. All right. And I want to show you geometrically what we're doing here. So we have our original integral, and I have it drawn here in a static format, but I'll let you see it in Desmos, our lovely program that we're going to use constantly for things like this. Okay, so for the original function, 2 times 2x plus 1, I wanted to integrate it from 0 until 2. So when I find the integral of that function, Notice, by the way, if you just name the function f of x, find the integral, you can just say, hey, find me that integral from 0 to 2 of f of x dx. And lo and behold, it's 12. Right? That's the original function. But we didn't do the original function. We did this function. Let me turn on the graph. Sorry, there it is. That's the function we did. So we went u of x is equal to x, right? So that was our substitution. Well, 2x plus 1. But we found this integral. And notice that this integral from 1 till 5, and I called it z, but whatever, is also equal to 12. Right? So this integral, which is what we did 1 to 5 u du, but 1 to 5 z to z doesn't really make any difference. It's because I already used up u up here, right? But it works. They're both 12. You can see that this blue shaded region and this pink shaded region are exactly the same thing, which is what I'm showing you in the notes. So this is the original integral. This would be 12. So this would be the integral of 4x plus 2 dx, right? Because if I distributed the 2, 2 times 2 is 4, and so on. And this is the integral from 1 to 5. Oh, I'm sorry, this one was from 0 to 2. Sorry, that's important. So this is from 1 to 5 of u du. That's the one we ended up doing, and it also gave us 12. Right? So we never need to go back to x. You'll notice I never went back. I never put back in 0 and 2. Once I came up with these new limits, I was able to keep going. So you'll also make a note that I never needed to back substitute. Now I could have, but I didn't. And just a reminder, back substituting means put back in x. I never needed to do that. And it all worked out just fine. All right, so let's practice with a slightly more difficult problem. So, well, let's see here. It's pretty obvious what my u is. At least hopefully it's obvious. It's inside, right? The u is going to be, it's part of the inner part of a composite function. So u would be equal to x cubed plus 1. Now the derivative of that would be 3x squared dx. Well, I want the x squared and I want the dx, but I don't want the 3. I actually want a 2 instead. So I'm going to put 1/3 du is equal to x squared dx. All right, there we go. So I'll be able to do 1/3 du. I'll be able to put in u. Wonderful. But the trick is that I can't use the 1, right? So when I rewrite this integral, I'm going to be able to do square root of u. No problem. I'm going to be able to say 1/3 du. No problem. But what I can't say, oh, and I've got a 2 sitting there. That 2 never went anywhere, so I'm just going to stick it right there. That's fine. All right, so the 2 is still sitting there. That's these two pieces, the x squared and the dx, make the 1/3 du, and the square root of u. But if I write 1 and 2, I am wrong. I will be marked wrong, and everything I do will be wrong, right? Not the integral, but everything after that. So I have to put in my new values. So when x was equal to 1, u of 1, it'd be 1 cubed plus 1, which is 2. So my lower number is actually 2. When x was equal to 2, u of 2 is 2 cubed plus 1, which is 8 plus 1, which is 9. So those are my values. So I'm going to go from 2 to 9. Not 1 and 2, right? Writing 1 and 2 is wrong. Wrong, wrong, wrong. I have to put in the correct values for u. It has to all be u values. All right, well then now that I'm here, this isn't so bad. So let's see here. First thing I'm going to do is take the 2 and the 3rd and pull them out. They're constants, so I'm just going to rewrite that. And then 2 to 9, this is u to the 1/2 power du. Okay. So then I'm going to integrate. So that's 2/3. The integral of u to the 1/2 would be u to the 3/2, because you add 1, and then you multiply by the reciprocal. So you multiply by another 2/3. And then you're going to take this from 2 to 9. Matter of fact, I will keep those colors in. Sorry. I decided to drop the green and the orange, but I'm going to keep the pink and the blue. Sorry if you're colorblind. It won't make any difference, but to me it matters. All right. Now, the 2/3 and the 2/3. This 2/3 in here is a constant. So we learned a long time ago we can just pull constants out from this calculation, right? It's the same thing as factoring. So that would be 4/9 because 2 times 2 is 4, 3 times 3 is 9, no problem. And then I'm going to put 9 to the 3/2 minus 2 to the 3/2. Okay. I mean, technically that's an answer. It's not simplified, but it's an answer. Right? This is not simplified. But that's fine. I mean, I could still come up with a decimal for it, right? In Desmos, if I wanted to find a decimal for that, let me show you. Let me just make a new graph. So in Desmos, if you want to do this, you just type 4 divided by 9 times, let's see, 9 to the 3/2 minus 2 to the 3/2. There we go. It's about 10.743 figure. That's fine. So we can come up with a decimal. Of course, we always give credit where credit is due to Desmos. That's lovely. Now, if you wanted to simplify this a little bit, we could, because technically this is 4/9 times, technically that's the square root of 9 cubed minus 2 to the 3rd, and then the square root of that. I'm doing slightly different methods because, well, I need slightly different results. So square root of 9, the 2 part there makes the square root. So the square root of 9 is 3. So this is 4/9. This is 3 to the 3rd. And I didn't do that over here. I used the other trick. Let me just remind everybody really quick. A to the p divided by q is either the qth root of a to the p, or it's the qth root of a to the p, right? It doesn't really make any difference. They're one and the same. So I'm using actually both of those for this step, because this one I know the square root of 9 will work out, and this one I know the square root of 2 will not. So I made that 8. So this is the square root of 8. So this is 27. So 4/9 times 27 minus 2 square root of 2. That's the simplified version. Of those three, the simplified version is the version I would ask for the least, but nevertheless, it's useful to know how to find it.